Okay, so we'll get started. Here I'm finishing up um, fat analysis, and then we'll move on to protein analysis today. So we already covered succid and Maginer last time, last Friday, and some of you started the lab already, and some of you will finish the lab on Wednesday. So I'm not going to give you any review on that because you will be doing it in the lab. So moving on, I'm still talking about solvent-assisted extractions and solvent-based fat analysis methods. So this is another solvent-based extraction method, and usually it's linked with analytical analysis. So we extract the fat, and sometimes we can link it directly with GC analysis. So what happens here is we use supercritical fluid extraction. In this case, normally CO2 is used above the critical temperature and pressure. So this means that the temperature and pressure is above where the CO2 is gas, so the CO2 becomes liquid, and it gets pumped as liquid into the cell compartment that you see here, and that's where your sample is. So the solvent, which is now SO2, CO2, sorry, in the liquid form goes into the sample cell and the fat gets extracted. And it can be continuous or semi-continuous. So here you can leave the solvent along with the sample in the cell where the solvent solubilizes the fat. And after that, it gets moved. You open the valve here and the solvent moves along with the fat into the collection tube. And once it's collected in this tube, it goes back to atmospheric temperature and pressure. So the CO2 becomes gas again and evaporates, and what's left is your lipid component. Okay, so that is one, elevated pressure and temperature. Another elevated pressure and temperature is the accelerated solvent extraction method. In this case, you don't have CO2, you have organic solvent, nonpolar organic solvent. But what you do is you apply pressure to the system so that the solvent does not evaporate anymore at the low temperature. For example, if you're using PET ether, let's say, its boiling point is 36 to 38. Now the boiling point will be higher. So you enhance the efficiency by having the solvent not evaporate so fast, just soak the sample longer and extract the fat more efficient. So here's the setup. So you have your pump and the solvent under pressure, and you're purging with nitrogen to not have any oxygen in there. And you open that valve, then your solvent comes here and you have high temperatures and pressures here. And again, you can operate in a static mode or dynamic mode. That means this valve is closed, it will be static. So the solvent is soaking the sample and solubilizing your fat. And when you open that valve, then it becomes continuous where the solvent goes through, solubilize your fat, and comes out into your collection vessel. Here's also you will have solvent and sample, or solvent and lipid. In this case, you really have to evaporate the solvent after you collect it because the solvent is your non-polar organic solvent. You have to heat it up in somehow 34 to 38 degrees C to get that solvent out. Okay, so these are our solvent-based extraction methods. You have non-solvent-based wet extraction method. This here is the Backcook method for extraction, and it is done for dairy, mostly for dairy products. So you have a special flask. We call them Babcock flask. Backcook is probably not probably, is the professor from Wisconsin who developed this method. There's Babcook Hall in Wisconsin, um, in the food science department, so named after Babcock. So basically, what you do is very simple method. So you have these different flasks for different dairy products. So this flask here, A is for milk, B is for cream, and C for cheese. The cheese, obviously, you see here there's an opening, so you can put in the cheese more easily than having to go through a narrow neck to put in your sample. So again, it's a straightforward method. So you put in your sample and you add a specific volume of H2SO4. So if you have milk, you also put a specific volume of milk. Usually it's about 17.6 or zero point 0.8. It's a very specific volume, milliliter of your sample, and about an equivalent amount of H2SO4, concentrated H2SO4. So it's a concentrated acid. So when you have your concentrated acid, again, about 17.6 or 0.8 milliliter, I can't remember the exact volume, but it's around that ballpark number. So you have your sample, let's say milk, you add to it the H2SO4, it's an exothermic reaction. So you have a really strong acid and you put it with the sample, the acid is going to start digesting your sample. And what happens is you start having heat generated. So the heat is going to help with the separation of fat. So the fat, because it has lower density than your milk, other milk components or water in milk, it's going to rise to the top. So the heat is going to help with the separation. What happens, you centrifuge, there's specific centrifuge for that, and you get very nice separation. And the measurement of fat, so the fat will be on top. You can see here it's graduated, so you can actually take the measurement, starts from 0, goes up to 20 ml, so you can read the volume of your fat. So it's a volumetric method. It's not a gravimetric method. If you remember, we talked about Soxhlet and vagina being gravimetric. You actually take the weight of your sample and then weight of the fat, or the difference in weight in your sample will be the weight of the fat. So gravimetric here is volumetric. That means you're taking the volume of fat. And you have the volume of the milk sample starting. You can convert the volume to grams by knowing the density. If you know the density of milk and you know the density of fat, you can convert the percentage in the volume to percentage in gram. So you can do that calculation. We have an example calculation later on. So Gerber method is very similar to Babcock, except you have two slightly different flask shape, but you have the same principle. H2SO4 is used, and this is used mostly if you have sugar that will char. That means you get the burning of the sugar, so you get charring on the glass. It would be hard to take measurements to read the volume. So what they add here is they add amyl alcohol to basically reduce the charring of sugars. So you will be able to read the volume of the fat better that way. So but basically it's the same principle. So let's do some practice here, because both methods are volumetric. And if we want to convert the percent volume to percent on a weight basis, you would need the density of the fat and the density of the milk. So density of the fat is 0.9 and density of the milk is 1.032, and the unit is grams per milliliter. And you have, based on volume, you get the volume percentage of 3.55 fat on volume to volume. So that means 3.55 milliliters of fat in 100 milliliter of milk. What would be the percentage on weight basis? That means grams per 100 grams. So that's what you need to get. So you have the given, the density. You have the amount in milliliters, so 3.55 milliliters of fat in 100 milliliters of milk. So do the calculations and let me know what you find out. Okay, so we have an answer, 4%. Let's see what we get. So not quite. Anybody got the different answer? Yes. So we're getting 3.1, which is the correct answer. So what you really need to do is convert the milliliters to grams. So first of all, you have 3.55 milliliters of fat. So you convert that to grams. Density equal mass over volume. You have the volume, you can calculate the mass. And then the same thing you do, you have 3.55 milliliters and 100 milliliters milk. So what's the weight of 100 milliliters milk? So the weight of 100 milliliters milk is basically density times the volume. You get the weight. So now you have 3.195 grams in 1.032 grams. So the ratio times 100 is the percentage in grams. Okay, so 3.1 grams per 100 grams. Okay, so the last here slide I have is you can also use instrument-based methods to determine fat content. We can do IR spectroscopy, near IR, mid IR. So you can determine the amount of fat based on the absorption of IR radiation by the different fat components or the functional groups in fat. So this method, you have to use calibration. It has to be calibrated often against an official method of analysis, which either is a Medriner or a socket. So it has to be calibrated with different standards, different concentrations. So remember that. It's a quick method. Once it's calibrated, you get quick results. So you can use both NIR and mid-IR. So NIR is used for a wide range of products and samples. Mid-IR is very commonly used for dairy products. Phosphate method, It's basically you determine based on the specific gravity of the sample of a sample solvent extract. So you extract the sample in a solvent to get the fat in the solvent, and then you measure the specific gravity of that extract in the solvent. There's specific solvent that is used, and there are specific conversion charts that will convert specific gravity to percent fat. Okay, very simple, straightforward. It's not necessarily used as an official method of analysis. NMR is very accurate and precise method. It is complex in a sense, the instrument and analyzing the spectra, but it's very simple in terms of putting the sample in and getting the value for percent fat. It's very simple, very rapid, but it's expensive. If you have NMR, that's great, but not every lab has NMR capabilities. Okay, so this ends the fat analysis. Any questions while I convert to the next segment here? Go. Any questions? Anything that you'd like to talk about, ask before moving on? Okay. Continuing with proximate analysis, and that is now protein analysis. A lot of the methods, there's a lot of methods for protein determination. And every method is based on quantitating a different component in proteins, or the analysis is based on a specific component or characteristic of the protein. And here is just a reminder, we do a lot of, for research, for example, we do a lot of looking at protein content in solution, in extracts. So we have clear solutions. So we use 280 nanometer as our wavelength to quantitate protein. So it's a common UV absorption wavelength for protein. So what components of the protein absorb at 280? So what do you say here? Aromatic amino acids, aliphatic amino acids, tryptophan. What absorbs at 280? Remember your food chemistry here. I'm sure this was covered somewhere. Yes, Michelle? You know not A? Okay. Shushan, right? You think A and B? Okay. Let's see what else we're getting here. All right. So I see people say F. A lot of F's there. F is the correct. So, correct. Aromatic amino acid. Aromatic structure, whether it's an amino acid or any other components. If you remember isoflavones, they have aromatic structure. So aromatic structure absorb UV radiation. It can, every different aromatic structure has different lambda max, but if you have an aromatic structure, you have an absorption in the UV spectrum. Aliphatic amino acids do not absorb UV at 280. So aliphatic amino acid, with aliphatic, what do we mean? The R group is a chain that is not aromatic chain. That's the aliphatic definition of it. So your R group is a chain, a hydrocarbon chain. It might have other functional groups, but it does not have an aromatic structure. Tryptophan is an aromatic amino acid. Here they are. So you have 3 aromatic amino acids among the 22 amino acids. So these are tyrosine, tryptophan, phenylalanine. So this aromatic structure in each of these amino acids allow them to absorb UV light, particularly at 280. Okay. The aliphatic amino acids down there, you don't see an aromatic structure, proline here is not an aromatic structure. It's a closed ring, but it's not an aromatic structure. Okay, so that's one thing. Let's see. The following is true about a peptide bond. It is a covalent bond. It's a bond between the carboxyl group of two amino acids. It is the bond between the amino groups of two amino acids. Again, this is part from your food chemistry. Why do I care about peptide bonds? Because peptide bonds absorb UV radiation at 220 nanometer. Coleman? A and C, let's see. A is correct, C is not correct. So A, it is a covalent bond, but it's kind of confusing. Is it a bond between carboxyl groups? Is it a bond between amino groups? It's actually a bond between the carboxyl group and amino group. So it's a bond between a carboxyl group of one end of an amino acid to the amine group of the other amino acid. So that is your peptide bond. It's a very rigid peptide bond, doesn't have much of a flexibility in movement, and it vibrates, and the vibration of the peptide bond is measured at 220 nanometers. So if you are measuring a protein solution, and you know it's protein, it's not a peptide, so it's not broken down, it's not hydrolyzed. You know that you will be able to measure it at 280 for sure, because all proteins have some amount of aromatic amino acids in them, tyrosine, tryptophan, adenine. Proteins have them at different concentration, but in general, all proteins have some sort of some combination of these amino acids. So all proteins theoretically absorb at 280. But peptides, not all peptides absorb at 280. So some peptides are made up of 3 amino acids, 4 amino acids, 10 amino acids. You might not have any aromatic amino acid in your peptide. So if you are measuring the protein content or the nitrogen content of a sample that is made up of a lot of broken down proteins, like a protein digest, you have to measure at 220, because that's when you're measuring based on the peptide bond. Otherwise, these peptides will not be detected. The small hydrolysate will not be detected, because not all of this, when you break the proteins, not every fragment is going to have aromatic amino acid in it.
I had a question come up in the chat. I'm not sure at what point, but measured at 280 or
Okay, so Chris is asking, measure at 280 or 220. A protein that is intact, you can measure at both, either 280 or 220, but it is recommended at 280 to measure when the protein is intact. But if you have a mixture of intact protein and digested protein, that you have a small fragments in there, not every fragment has potentially an aromatic amino acid. You break down the protein and you get different fragments, and not every fragment have an aromatic amino acid. So then you would have to measure at 220 if you're doing UV absorption measurement. Okay. Why is it important to analyze protein content? Like a question we ask for anything, for ash, for fat, moisture. Why is it important to analyze protein content? Yes, Al? Nutrition label, of course. We have to analyze for nutrition labeling. That is one reason, Michelle. Yes, definitely. So we want the protein content to list on the label, and we want the protein content to get all of the components that can be measured, so we can subtract from 100 and get carbohydrate. All right. So for nutrition labeling, we can sum both of these under nutrition labeling. Okay. What else? Can you think of any other reason we need to determine protein content? Is there a value for it anyway, Shushan? Infant formula. So for nutrition labeling as well. Okay, let's quality. Yes, quality analysis. So that's very important. Let me just show them up. So quality control, quality analysis, we need to monitor protein if we are claiming high protein, like for bodybuilders. Yes, if we're claiming a high protein, we need to make sure that during our process, we maintain a certain amount that we can claim a high protein. That's one example. But also, not only quality control for that purpose. So we have now a lot of demand for protein ingredients and protein use in different formulation. So you have something called soy protein isolate, soy protein concentrate, and pea protein isolate, pea protein concentrate. How do they get the label of a concentrate or an isolate? They get that label based on the protein content. So in the soy world, in the soy protein world, you cannot call an isolate unless it has 90% or higher protein content. You call a concentrate if it has 60% or higher. That is in the soy protein world. In the whey protein world, you can get whey protein concentrates anywhere between 30% protein to 80% protein. So you have a wider range for a concentrate, but whey protein isolate has to be 90% or higher. Okay, so in the pea protein world, it's different. If you have 80% protein, you call it protein isolate, pea protein isolate. So it gets really complicated and confusing depending on what protein ingredient it is, but that's why it's important to know what's the protein content so that you can label it or name it. It's an isolate, it's a concentrate, so that's an example. Okay, so the other three reasons are mostly for research purposes, analytical purposes. And also if we want to claim any biological activity. Well, this is not necessarily for research. If you have an enzyme is a protein, right? So if you have an assay and you need to use enzyme, you need to determine how much enzyme you use. And normally we report activity of an enzyme. So you need to know the activity per 1 gram of that enzyme or 1 gram of that protein, which is an enzyme. So we need to know the amount of protein, which is a purified enzyme, so that we can get the activity of it. And sometimes the biological activity is not necessarily enzymes. Sometimes you have antihypertensive peptides, which are components of a protein. And you want to know the activity, antihypertensive activity, or the antioxidant activity per gram of protein. So that's biological. So other is protein fractionation and purification that could be on a research basis or also could be on a large scale. And that is also related to the example I gave earlier is when you fractionate, you get an isolate, you want to know which, or a protein ingredient, you want to know which category you can label it, an isolate, a concentrate, and so on. We do that plot in our lab, we determine something called protein meal. From a start material, how much protein from the start original protein that we have in the original sample, how much protein we were able to extract using our method. So this is very important for the industry because we need to know which is the most efficient extraction method so they can get all of the protein out and not lose protein in the residue. That would be either animal feed or thrown away even. So they want to get all the value out. So protein is value. So they want to get it all the way out. So it's very important to determine mass balance. So they take measurements throughout to determine where that protein is and how much protein wind up in the end. Functional properties investigation. So again, this is very critical in the protein world. So how much protein do I need to form a gel? Okay. If it's gelatin, 1 gram, 1%, 1 gram and 100 ml can form a gel. If it is whey protein, potentially 5 to 10%, sometimes 5% is enough. If it's pea protein, sometimes 20% is not even enough to form a gel. So functional properties, how much of a protein I need to form a stable emulsion, how much I need of a protein to form a gel, how much do I need of a protein to form a good foam. So that's why it's very important to know protein content for functionality. Okay, methods. We're going to talk about different methods today. The two most common methods that are official methods of analysis and used to calibrate IR, for example, are the CalDER method and the DUMAS method. So the CalDER method and the DUMAS methods, both of them you will be doing in the lab next week, and you will be doing one of the research methods, which is Bradford assay. So we'll talk about all of these different, well, not all of them, but definitely CalDER and DUMAS, a little bit IR, and then a couple of the research methods we'll highlight as well. Okay, so I'll start off with CalDER. So CalDER is one of the oldest methods for analyzing protein content. It's heavily chemical-based method, and it measures the amount of nitrogen. Okay, so it doesn't measure protein, total protein, it measures total nitrogen, and we convert the total nitrogen to total protein. So it's based on, it involves digestion with an acid, neutralization and distillation with a base, and then again, titration with an acid. So we'll talk about all of the chemistry of these and the equation and calculation for protein content. So it does measure total nitrogen. However, we need to convert total nitrogen to total protein. So we have a conversion factor. So where does that conversion factor comes? It comes from knowing an approximation of total nitrogen per gram of protein or per 100 grams of protein. So every protein has different composition, right? So the different composition of the protein impact the percentage of nitrogen. Why is that? Every protein, you're going to argue, it has an amine group, it has a carboxyl group. Every amino acid in a protein has an amine group and a carboxyl group. But some amino acid has extra nitrogen in their chain. Can you tell me which amino acids have extra nitrogen, or which category of amino acid may have additional nitrogen in their R chain with chemistry? Yes, lysine is one of them. Thank you. So lysine is one of them. So you have 3 amino acids. We call them basic amino acids. You have lysine, arginine, histidine. So these are basic amino acids because they have an additional amine group in their R chain. So the composition of your amino acids within a protein dictates how much nitrogen you have. So the conversion factors for different protein sources is different. It's not the same. And if you don't know the percentage of nitrogen in that particular protein source, we use the common conversion factor, which is 6.25. It's common. It's giving you like 16. The 16 here is the 16% nitrogen in a protein. So it's giving you an average, an overall. 6.25 is the conversion, general conversion factor. For milk, for example, it's 6.38. It has less nitrogen percentage. It's less basic protein than a protein, for example, coming from wheat. Wheat has a conversion factor of 5.7. It has more basic amino acids. So The higher the percentage of nitrogen in a protein, the lower is your conversion factor. Okay, so the general one, when you don't know, or it's general, or maybe it's a formulated food product that has multiple protein components in it, coming from different sources, you just use 6.25 as a general rule. It's crude protein because not all nitrogen is coming from the protein. You might have nucleic acids from DNA. You might have some vitamins might have nitrogen in them. You might have urea that might cause nitrogen, nucleic acid, urea, vitamins. So you might have nitrogen sources that are not necessarily coming from your protein. So that's why it's a crude protein estimation method. It's estimation because you're taking all of the percent nitrogen that you're getting, all of the potential amines that you have, and you are saying all of them are proteins. No, not all of them are coming from protein. Okay. Nevertheless, it gives you a good estimation and it's a accurate method, it's a precise method. Although it's an estimation, it gives you a very good proximate estimation. Okay, so the main reactions that happen during the CalDER estimation are three reactions. Okay, so in an exam or a quiz, if I tell you what are the main steps of CalDER, you have to say digestion, neutralization slash distillation. So here in the second step, you have neutralization as well as distillation going on. And the last step is titration. Okay? So these are your three segments of CalDER, which you will be doing in the lab. So the digestion will unfortunately be done for you already because it takes a long time to digest. And then you will be doing the neutralization, distillation, and titration stuff. So the first step is the digestion step. It's very critical step because here in this case, you have your food sample, you weigh a certain amount of sample. It might range anywhere between 0.1 to 2 grams. It really depends on the capacity of your system, how big are the tubes. There's micro CalDER and there's the regular CalDER. And it also depends on how much nitrogen you have. So the higher nitrogen you have, depending on the size and volume of your tube, you might want to weigh less of your sample so that you don't have a lot of nitrogen and not enough space to have enough reagent to deal with them and to react. So you have your food sample, you add your sulfuric acid, in this case, a concentrated sulfuric acid, and you digest. So you put it on a heating block and you digest at really high temperatures. So with the sample, you add a catalyst. The catalyst, what it does, it speeds up the reaction and it also increases the boiling point of sulfuric acid. That's very important because you want to preserve the acid with the sample to have efficient digestion. If the acid evaporates, you'll have less acid to react with your sample. So you want to enhance the efficiency of this step. So you increase the boiling point of sulfuric acid with the addition of catalyst, copper selenide or sulfate sometimes, and potassium sulfate are your catalyst. So what happens here is the sulfuric acid reacts with the amine groups and form ammonium sulfate. So now we're following the nitrogen. You have to remember, the easy way to remember CalDER is to see where your nitrogen is going in the reaction. We're following the nitrogen because we are after analyzing nitrogen content. So hence it's in red, we're following the nitrogen. So you form ammonium sulfate. So the high acid concentration, so the concentrated acid is going to burn your food basically. So strong acid, you have heat, your organic matter is going to burn. So the rest of the components of the protein and other components will burn and oxidize, and you get CO2 gas, H2O gas, SO2 gas. So all of these will leave the sample. What remains in the flask is your ammonium sulfate with any excess acid. So that's why the next step is neutralization of that acid and the reaction of sodium hydroxide with ammonium sulfate. So we call this neutralization distillation. There are two things going on. You have neutralization of the acid and you have the reaction of NaOH with the ammonium sulfate. So now follow the ammonium. So the ammonium is going to become ammonia gas. And then you have a salt, sodium sulfate, and water. Okay, so now your ammonium sulfate reacts with NaOH and you get ammonia. Now we're following ammonia. We call it distillation because ammonia and H2O are going at under high temperature. Both of them are ammonia as gas, right? And water vapor is going to evaporate. You get water vapor, ammonia. So these are going to go up into a distiller and get distilled into a flask containing boric acid. So now we're following the ammonia reacting with boric acid. So the boric acid and ammonia, when they react, you get ammonium borate. That's a base. Okay, so you'll see a lot of colors in the reaction. It's very colorful reaction. So the boric acid, we will have an indicator in there. The indicator will be red in the acid and becomes yellow in with the base. So what you get then is your ammonium borate. Now it's basic. So what you do is you have your ammonium borate, you titrate with HCl back to boric acid. So we go from yellow to last drop, turning it pink. So number of moles at this point of, okay, let me stay by the computer. So number of moles of the acid of HCl at equilibrium at the last drop that turns pink, the number of moles of the acid will be equal the number of moles of ammonium. Because you have one ammonium, one borate, one borate, one acid. That means equimolar. So at equilibrium, you have 1 molar of ammonium equals 1 molar of HCl. So that's very important for later for calculations, that we will derive the equation together. Okay, let's hold on that equation. This is the system that you will be using. So you will be using the digestion block. So here we have special tubes, the CalDER tubes. Here you will weigh your sample. You would already weigh it on a wax paper. You put your pre-weighed sample in there with the wax paper. And you have the catalyst, you add the catalyst, and then you add H2SO4 to it. And you put it on the block. And you see here you have a system that is closed. It's exhaust system where the fumes are contained and it's under the hood. So you don't have all the fumes coming out. The fumes that have CO2 and SO2, you don't want to inhale any of that. So it's all closed exhaust system. We'll show you that in the lab. So what happens here, the sample gets digested. It turns dark black because it's burning. So everything turns dark black and then fumes, white fumes start coming out. So the color changes from dark black to brown to start getting some green color, green blue color to a very sky color blue. You'll go, why is it sky color blue? Because the catalyst is blue, it has copper in it. So you get a very nice clear blue solution. So if you take it out and you still have some blackish, brownish material, that means the digestion was not complete. When the digestion is complete, you get really clear sky blue solution. So at this point, this is the other unit that we will be using. So here you have your ammonium sulfate, you have some excess sulfur H2SO4, sulfuric acid. So what you do, we neutralize with NOH. So the NOH is going to neutralize excess acid and some of it is going to react with your ammonium sulfate. So you will have the reaction of ammonium sulfate with NOH. So you have here heating by steam. We inject steam, it heats the entire tube. Ammonia will evaporate, go out, and some water will also evaporate. That's why we add water also to the mix so that you have medium for the ammonia to be with. So the ammonia and the water vapor goes up here into the condenser and it condenses into a flask where we have our boric acid with methyl red indicator. So your indicator is going to convert, well, it will be pink at first because boric acid and the indicator will be pink. And as ammonia drips into your flask, you start seeing the pink going to orange, or not very bright orange, very light orange, and to yellow. And then you know you've gotten, you trapped your ammonia, and now you have ammonium borate. You take that flask and you titrate with HCl, a standardized 0.1 normal HCl. And then you titrate to get pink color back. We always run a blank. I'm going to stop here after talking about quickly about the blank. We always run a blank because you want to correct for any nitrogen that comes from the reagents we use or the wax paper that we use to weigh in our sample, from the catalyst, from H2SO4, from ammonia, from sodium hydroxide, any source of nitrogen, we have to correct for that. And you account for it during the calculation. So that's basically an illustration of the ammonia being released and trapped with ammonium borate. Trapped as ammonium borate by reacting with boric acid. This is a very old unit of CalDER. That's when I was a student. That's what I used. It's very, funky looking, but it does the job. So here is the digestion. And it's also linked to an exhaust system where it's kind of trapping the fume. So it gets digested here, and then the fume goes up and get collected here. And on the upper side is where we do the distillation. So not the distillation unit is up there. You don't see it in the picture. So it takes much longer time to distill than the few minutes we distill using the instrument we have in the lab. So spend many hours on CalDER before. Okay, so we titrate the calculation. I'll stop here and go over calculation first thing on Wednesday. All right, thank you all. Let me stop. And stop the recording here really quick.